In section 15, activity 3, we're asked to use the information that we've gathered from the point slope formula to create equations based on a model. So in question number 1, it says, to ride down an elevator, the floor number the elevator is at, f of t, is a linear function of the time in seconds t of the ride. Jim noted the times the elevator passed a particular floor. So here's the data. What that essentially means is at time 4 seconds into the journey, we're at floor number 16. 6 seconds into the journey, we're at floor number 14, and so on. What we're asked to do in part A is to compute the slope of the data. In order to do that, we have to figure out what the input is and what the output is. So looking at kind of the structure of the sentence, the floor number is a function of the time. Time is an input, and you're never going to have time where that's an output. All right, you cannot control time. So time is the input, and the output is the floor number that we're at. So this is the output, and this is the input. What I need to do then is find the slope, which is the change in the output over the change in the input. So the output, I just picked 2 random points here. I just went with these guys right here. From 16 to 14, that's a -2 change for the output. And for the input, I'm going from 4 to 6. That's a +2. So my slope then is -2 divided by +2, or -1. We're also asked to include units in our answer, and essentially that means what does the output mean in the problem? Well, F is floors, so it's -1 floors, and then per unit time, which in this case is seconds. That's our units. What this essentially means is every second that passes, we will fall 1 floor. In part B, we're asked to write an equation for the floor pass as a function of time. So again, the floor pass is the output, the time is the input. Now again, with y minus y1 equals m times x minus x1, the y and the y's were the outputs and the x's were the inputs. We're going to follow the same structure for this equation. Since f is the output, we're going to start it over here. Because t is the input, we're going to end with it over here. So I picked any point. It really doesn't matter which one you pick, as long as you're picking matching values. So I've got the time and the floor number. So I took f minus the floor number, which is 16, equals our slope, which we just found, times t minus the t value, which is 4. Ideally, what we're going to do next is solve for f, because we want to have an equation that has f by itself, a function. So the ideal way to do this is to distribute the -1 to the t and the -4, making it -t plus 4. And then we add 16. So this is my new equation. There's another purpose for me doing this, and that I have to do some more things with the function later in part C and part D. So if I have f by itself, it makes it a whole lot easier than having to rearrange this equation every time I need to do something with it. On part C, it says, after how many seconds will the elevator reach the ground floor? And for our purposes, we're going to call the ground floor 0. So that's f. F is 0. So I set 0 equal to -t plus 20. Now, we got a couple ways we can solve this. One is to subtract 20 and then divide by -1. But probably the easiest way is to just add t to both sides. And what we end up with is t equals 20 seconds. Which makes sense because at 18 seconds we were on floor 2, and we're dropping 1 floor every second. And then in part D, what floor will the elevator be passing after 9 seconds? We're going to plug 9 into the function, -9 plus 20, and we'll get 11. Again, that makes sense because between 6 and 14, time 9 falls in there, and the floors are 14 and 6, so between there we get floor 11. Now this one was kind of the same thing, but I'll kind of quickly run through the answers here. Again, change in output over change in input, so it's 0.8 over 40, which we want to reduce. Then we write the equation for that. Again, selecting the point 2.4 and 120, and plugging those values in. And then part C and part D, we just rearrange that equation. Plug 12 in for the gallons, and find the number of miles. But I want to take a look at a graph because it's kind of a similar structure, but a little bit different look. The pressure of a gas is the output. The temperature is the input. Now, even if I didn't have this verbal description, I could tell from the graph itself. On the horizontal axis, we have temperature. That's our input. Horizontal will be your input. And then the vertical will be our output. In this case, it's pressure. That's kind of tough to read here, but pressure is listed in pascals, and then the temperature is listed in degrees Celsius. So to find the slope of the data, we're essentially looking for what was our change in our vertical over the change in the horizontal between two consecutive points. So we've got a point here, 224, and 20, 25. So my vertical change is a +1, that's the output change, and my horizontal change is a +10, that's my change in input. And again, the vertical was pascals, and the horizontal was degrees Celsius. So it's 1/10 pascals per degree Celsius. In part B, we're writing the equation of the line. I picked the point 1024 because it was the easiest one to use. I already know what those points were. I already figured those out. So the y-coordinate, or I'm sorry, the p-coordinate is 24. That's the output. So p minus 24 equals 1/10. And then the t minus 10 would be our temperature. And we can rearrange that for p, distribute the 1/10, and then add 24 to both sides. And we end up getting 1/10 T plus 23. Then in part C, we're asked to find the pressure at a particular temperature. So we plug that in to T. 1/10 of 55 plus 23 is 28.5. And then the same thing for 0. 1/10 of 0 is 0, and add 23, we get 23. In part D, take that equation. We know the pressure. Now we want to know the temperature that makes it happen. So plug 28 in for pascals and solve it. And we end up getting T equals 50 degrees Celsius.